Suppose we have to search for a node in a binary search tree. By definition, we know that in a binary search tree, all the values in the left subtree of the root node will have a value which is less than the value contained at the root node. And all values in the right subtree of the root node will have values greater than the value at the root node. Now suppose if we have to look for a value which is 65, and we are assuming that this binary tree is just containing integers. So if we have to look for a value 65, this is the data that we are searching for, we will first compare it with the root node. Since 65 is larger than the value at root node, we know that we will have to search the right subtree to look for this value 65. So recursively now we are going to check each and every node, and depending on whether the value that we are looking for is greater than or smaller than the root node, now we will go in that particular direction. So now when we traverse the right subtree, we come to node 70. 65 is less than node 70. That means we have to traverse the left subtree. So we check the root node now, 59. This 59 is now the root node of the left subtree of the node containing 70. Now we compare this value 65 with the root node 59. We know that 65 is greater than 59, so we will now traverse the right subtree of the root node 59. Now this becomes the root node. And when we compare 65 with our value at root node, we know that we have found a match. So recursively we are seeing that at each and every node, we are reducing the search space by 2. So initially if we had n nodes, if now we start going towards the right subtree and assuming that the tree is balanced, and we have actually divided the search space by 2. So now we would be looking actually at only n by 2 nodes. Once we reach here, again when we take the decision, we know that we have to look again only on one side of the tree. So this becomes n by 4 till the time we reach that one node that we are looking for. So for a binary search tree, the search complexity is log n in case it is a balanced tree. And what is a balanced tree? You can check my earlier videos for that. But if the tree is not balanced, if it is skewed on one side, if the tree is skewed on one side, if it is left skewed or right skewed, then the complexity would be order of n. Let's take another example. We are looking for a value 16. Compare it with the root node. Since it is less, we know we have to traverse the left subtree. So we check again with the root node 32. It is less than 32. Again we traverse the left subtree. We compare with root node 22. It is less than 22. Traverse the left subtree. Check with root node 14. It is larger than 14, so now we traverse the right subtree till the time we reach the node with value 16. Similarly, you can check with value 43. You will find that even after traversing, after you have reached this node over here, there are no left and right subchild of this node, and that means this value 43 is not available in the tree. So what is the code for searching a tree? First of all, if we are using a linked list kind of data structure for this, where we are having nodes for storing the values at each node in the tree, then we can define a structure which is BST node, which will have the data. We are assuming that it is storing integer data. Also, it will be having a pointer to the left node and a pointer to the right node. So each node would be of this type, where we would have the data, a pointer to the left node and a pointer to the right child. We know that a binary tree can have at most 2 children. It can have either 0 or 1 or 2 children. So each node will have a pointer to the left child and a pointer to the right child. In case there is no child, then that pointer would be having a null value. So if we want to do a search operation in a tree, so this is a function that we have created, and this is going to return a pointer which is of this BST node type only, because that is going to return the address of the node where that value is existing. Suppose that value that we are looking for is 5. First of all, we will send the address of the root node of the tree. So this is the pointer to the root node, and we will also send the value that we are searching for. Suppose this is 5. First, what we have to do is check whether root is null or not. If root is null, that implies that it is an empty tree, and in that case we will simply return the root, that means the null value, and say that this does not exist. Or if root data is equal to the value that we are looking for. So suppose at this root only we find the value that we were looking for, then we will simply return the address of that root. So this is our returning condition. Because we are using recursion, we have to have a returning condition as well. If this value is not found at the root, we will check whether the value is less than the root data or not. In our case, yes, it is less than the data which is available at the root. So in that case, recursively we are going to call now a traversal or a search operation on the left subtree. And if we want to search the left subtree, we will have to give the address of this node now. And this address is available on the left pointer of the root node. So we pass this address root arrow left and the value that we are looking for. When this root arrow left is passed, that means we are passing the address of this node 3. So this function, it will start running again. So now we have passed the address of the left child of root node 7. Again we will check whether root is null, no it is not, or root data is equal to the value that we are looking for. The value at this root node is now 3. This is not the value we are looking for. So we come to the next statement. Is the value less than the root data? No, we are looking for a value 5, which is greater than the value at the root node. The root node is having a value 3 now. So we come to this statement. That means our value that we are looking for is greater than the value at the root node. So again we will call the search function again, and now we have to traverse the right subtree of the root node. So we will give the pointer to the right child of the root node. So the right child of the root node will help us in traversing the right subtree of the root node. So now what we have done is we have given the pointer to the right subtree of the node root node 3. So we have passed the address of this node. This node, root node, is again received over here, this root pointer. And the value that we were looking for is again received. Again we check if root is equal to null, no it is not, or root data is equal to the value that we were looking for. Yes, the value that we were looking for is 5, and now we have found it. So we will return the root address. That means we are going to return the address of this node which is containing 5, and it will be passed to the function which had called this search function. So this is how the search operation will take place. And as I have explained earlier also, that since each time the search space is being reduced by half in a balanced tree, so the search complexity is log n. If it is a skewed tree, if it is left skewed or a right skewed tree, then the complexity would be order of n, because then in that case you will have to search through all nodes in the worst case.